In the last lecture, we learnt about the mathematical concept of tensor product. We saw how to define tensor product of two vector spaces V and W. If the dimension of V was M, the dimension of W was N, the tensor product space had dimension Mn, and there was an easy way to define an orthonormal basis of this tensor product space. This was our introduction. We also emphasized how to define the inner product in this space V tensor W that gives it a structure of an inner product space or Hilbert space for our purposes. Not just that, the final thing was to define the operators over this tensor product space. We said that the operators on the space act naturally, they act on the respective systems. Looking at these definitions, this tensor product seems to capture two composite systems very well, and that's how our fourth postulate is defined. What does it say? To be precise, suppose the state space of Alice, let's say we have two parties, first is Alice, her state space is HA, and Bob is HB. So we have two systems, one system is with Alice, one system is with Bob. The state space of Alice is HA, for Bob it is HB. In this case, the state space of the combined system, this is what we are interested in. So the state space of combined system is, no price for guessing, HA tensor HB. If Alice's state is vector ket A and Bob's is ket B, then their combined state is again simply A tensor B. Notice here we are just giving a description one way. If we know the state of Alice and Bob, then we can write the state of the combined system. Here we do not mention what is the state of the combined system. Given the state of the combined system, what is the state of Alice or Bob? This we are going to go into detail at the end of this video. Before that, this A tensor B, sometimes in shorthand, we just write like that. This has been told to you before. This is postulate 4. What does it tell you? It expresses the state space of a composite system in terms of the state space of the individual systems. The individual systems were HA and HB, then the combined system have state space HA tensor HB. If we know the basic state of Alice and if we know a basic state of Bob, then we know the combined state also. Though these are not the only states in HA tensor HB, and we will talk about it later. But before that, simple thing, if operator A is applied to state A by Alice, again look at this as two systems in parallel. We apply A, matrix A to state A, this is done by Alice, and B to state B by Bob. If this happens, mathematically we will capture it by saying this. So on the PIC system, the state is A tensor B, and the operator applied is capital A tensor capital B. The final state should be this. It follows the natural laws which we expect it to follow. A small matter about convention. Generally from context, it will be clear which system is which, in the sense that when I write A tensor B, it would be clear that this belongs to Alice, this belongs to Bob. If there are any confusions, then I used subscript to get rid of that confusion. So if I write like this, sometimes it means that I'm applying A to my system 1 and B to system 2. But most of the time, it will be clear from the context when I write a tensor product. Let's take an example. I will take an example of k qubits. What can we say about the state of k qubits? We have studied the state of 1 qubit in detail after the first postulate. What about k qubits? Let us go slowly. 1 qubit is an element of C square. What about 2 qubits? From the fourth postulate, it tells us that 2 qubits, the state space should be C square tensor C square, which will be equal to C to the power 4. In this case, we are going to have 4 basic states, 0, 1, 1, 0, and 1, 1. We shall start with 0, 0, then 0, 1, 1, 0, 1, 1. These 4 are the basic states, and these span C to the 4. We can extend this analogy more. For k qubits, my state would be C to the 2 to the k. It will have 2 to the power k basis states. This is the dimension for a k qubit system. Now, since there are 2 to the power k basis states, a simple way to write the standard basis, as we have been doing, is this. Though this is not a great way to write it, because this loses the structure of individual qubits. In most of the cases, when there are k qubits, we would prefer to write our basis in terms of k length strings. You can easily check that these are 2 to the k possible strings. They are element of 0, 1 to the k. For each of them, I define a basis state. And now any v element of C to the power 2 to the k is summation alpha I should say, sorry, I equal to 0 to 2 to the k minus 1, the amplitude alpha I, and then I would say binary representation of I. This bin I will represent one string of length 2 to the power, sorry, one string of length k. So we prefer to write our state in terms of these 0, 0, 0, 0, 1, 1, 1, 1 vectors as compared to 0, 1 to the k minus 1, because when it's a product state, we see it clearly that things are in product, and it keeps the structure of k qubits alive. There is another thing to notice here. For k qubits, the dimension of the system becomes 2 to the k. So we have an exponential blow up in the state space, or the dimension of the state space. If there are k qubits, and if I want to describe their state, I need 2 to the power k numbers, to the power k amplitudes to describe those k qubits, because they are to the power k dimension, and for every dimension I will have a complex number. And this is very hard to keep track of. If someone has k qubits and they are playing with these k qubits on a quantum computer, then if you want to just make sure what is happening, we have to take care of the k amplitudes. This, in some sense, tells you the problem with classical simulation of a quantum computer. To simulate, you have to keep track of to the power k amplitudes, which takes a lot of space and a lot of time. And that's the reason why classical simulation of a quantum computer is possible, though very, very expensive. We come to the final concept today, but very, very important, known as entanglement, which arises from the simple property of tensor product. What is entanglement? The state of the combined system. So this is in opposite direction of the postulate. If we knew the state of the individual system, we knew the state of the combined system. Entanglement tells us, because of the tensor product structure, state of the combined system need not give us state of the individual system. If I tell you what is the state of Alice and Bob, sometimes you will not be able to tell me what is the state of Alice and what is the state of Bob. For example, let us say that Alice has 1 qubit, Bob has 1 qubit, then the combined system we just checked is of 2 qubit and the Hilbert space will be C to the 4. This has 4 basis elements, 0, 0, 0, 1, 1, 0 and 1, 1, and any linear combination with the length 1 would be a possible state, combined state of Alice and Bob. So look at this magical state. There is a good reason why I am calling it magical. These are called Bell states. Anyone who studies quantum mechanics or quantum computing keeps encountering these states very, very often. So this is a particular Bell state. If I take a minus, is also Bell states, but what is important about this? Notice the structure. Claim is there is no way to write the state, I called it psi, Bell state, as a tensor product of state of Alice and state of Bob. Tensor product of two states. That basically means psi is not equal to A tensor B for any A comma B. This means I have allowed the combined system to be in this state. Let me once again write it. It's better that you see it as many times as possible. So this state is allowed for a combined system, but if something is in this combined state, you cannot figure out the state of Alice or the state of Bob. This is just their combined state. This is what we know. Their states are entangled. They cannot be written apart. That's called entanglement. This is going to be a very, very important concept. You will see, and this is also in some sense maximally entangled state, but it's very hard to define entanglement quantitatively. I showed you some example of a state which is entangled, but if I ask, is it very entangled, is it less entangled or something? These are all big research questions. People have partial answers to those, some measures are there, but still we don't know how to quantitatively measure entanglement. Though everyone agrees that these states 0, 0 plus 1, 1 by root 2 are very entangled, and they use them to show properties of a lot of physical phenomena. So it seems that in nature we can make these states. There are systems whose states look like this and they behave in an entangled manner. Now we know that there are some states which can't be written as A tensor B. Before I go into that, this claim I will leave it as an exercise. You can verify it. You can take two states A tensor B. There are two variables, and then multiply, take the tensor product, and you will see that they cannot be equal to psi. Easy claim to prove. Anyway, so now there are states which are not, can be written as A tensor B, but they can definitely be written as a linear combination. Again, easy to prove that I can write any state in this form, AI tensor BI, where summation goes from 1 to mn. I need mn terms here. That just follows by writing it in the basis. You can convince yourself, again, an easy exercise. It turns out that you can actually write it with much less terms. So instead of mn, you just need min of m comma n terms, and you can write any psi as a linear tensor product of these many terms. This is known as Schmidt decomposition. Another name for it is singular value decomposition. I will not go into detail of this. Feel free to look at this by yourself, but this is a very, very interesting decomposition. Trivially, it seems that we need mn terms like this to write psi, but even this much suffices. Thank you.